Good afternoon, and welcome to the science portion of today's briefings about NASA's new mission to study the sky of our nearest celestial neighbor, the Moon. The mission is called the Lunar Atmosphere and Dust Environment Explorer, or LADEE. I'm Rachel Hoover in the Public Affairs Office at NASA's Ames Research Center in Moffett Field, California, where the mission was designed, tested, integrated, and will be managed after launch. Earlier today, we heard from LADEE team members about the spacecraft design, its ride into space, and the conditions leading up to tomorrow night's launch at 11:27 p.m. Eastern, right here from NASA's Wallops Flight Facility in Virginia. Now we'll turn our attention to the science goals of the mission and a lunar laser communications demonstration on board. Before I turn our attention to the panel, I'd like to take a moment to point out that you can learn more about the mission by visiting us online at www.nasa.gov/LADEE, or by following us on social media, including Twitter, at NASALADEE. In a moment, we'll hear brief presentations from our panel, and then we'll open it up to questions here at NASA Wallops, from NASA Field Centers, and participants joining us from the phone. It is now my pleasure to introduce today's panel. Joining us today is Sarah Noble, LADEE Program Scientist from NASA Headquarters. Rick Elphick, LADEE Project Scientist at NASA Ames Research Center. And Don Cornwell, the Lunar Laser Communications Demonstration Mission Manager from NASA's Goddard Space Flight Center in Greenbelt, Maryland. And with that, I'd like to pass it over to our panel.
Thanks, Rachel. I'd like to give you guys a quick overview of the science of LADEE. LADEE has two major science goals to understand the lunar atmosphere as well as the dust environment around the moon. And I think sometimes we get a little surprised when we start talking about a lunar atmosphere, because most of us were taught in school that the moon doesn't actually have an atmosphere. It does, but it's very, very thin. It's so thin that the individual molecules that make up the atmosphere never see each other. They don't interact, they don't collide. This is something we call an exosphere. And if I can get the first slide up. Yes. The Earth actually has an exosphere as well, but in fact you have to go out past where the International Space Station orbits before you get to this condition where the molecules are so far apart they don't collide. On the moon, that actually happens right at the surface. So the term we use for this class of atmosphere is a surface boundary exosphere. And in fact, the moon is not the only example we have. Mercury, a lot of the moons of outer planets, as well as some of the larger asteroids in our solar system, all have surface boundary exospheres. It turns out to be the most common class of atmosphere we have, and yet it's one that we don't really know very much about. So LADEE is a really great opportunity to go to learn not only about the moon, but about many of the bodies in our solar system. It's also a really good time for us to go and be working this mission. The moon, because the exosphere of the moon is so thin and so delicate, it's easily disturbed by things like spacecraft landings. And the moon has been pretty quiet lately in terms of landings. We haven't landed anything there for a few decades, but that's going to change. There are a number of countries and even some private companies who are looking to land things on the moon in the upcoming years. And so now is a really good time while the moon's atmosphere is still sort of pristine in its natural state for us to go and learn about it before we go and impact it. The D in LADEE stands for dust. Our other major science goal is to understand the dust environment. If I can get the second visual. And we've actually had questions about the dust environment on the moon since even before Apollo. On the left here, you can see some images from the Surveyor spacecraft, which saw this strange thing on the horizon just before sunrise, this sort of glow. And we think that actually might be due to dust getting lofted into the atmosphere and reflecting the light. The Apollo astronauts also saw this horizon glow. On the right there is a sketch from Gene Cernan's notebook, Apollo 17 astronaut, who not only saw that horizon glow, he saw these things that he called streamers going up high into the atmosphere, tens of kilometers, which we also think is due to the dust. So we have three instruments on LADEE. If I can get my third visual. We have three instruments on LADEE in which to look at our two science goals. There is the Lunar Dust Experiment, designed and built by the University of Colorado, which will look at individual dust grains in situ. There's a Neutral Mass Spectrometer, NMS, designed and built at NASA Goddard Space Flight Center, which will look at the atmosphere. And finally, there's a UV spectrometer. Not the first spectrometer we've sent to the moon. We've sent many spectrometers there, but generally, when you send a spectrometer, it's looking down at the surface to look at the minerals that make up the moon itself. We'll actually be looking sideways through the atmosphere and the dust to understand what's going on just above the surface. So that's a quick look at our science payload. I'm going to turn it over to Rick now so he can give you a more in-depth view.
Well, as Sarah just told you, the LADEE mission is about, it's a tale of two mysteries. The first being the thin, tenuous, very exotic lunar atmosphere, utterly unlike our own. And the second being this mysterious lofted substance, purportedly dust, that the Apollo astronauts saw above the surface. And so in the first video that I'll show you, it kind of illustrates the second mystery. There's Laddie in orbit around the moon, and the sun going down over the horizon, and you can see this glow behind the spacecraft, and that's meant to represent this possible dust cloud that exists around the moon near the terminator of the moon, near the dark sunlit portion. So those are the things that Laddie is equipped to look at and try to explain. And this next video shows you Laddie pirouetting in space, and I want to use this video to kind of illustrate the different instruments and their locations on the spacecraft. So coming up actually is Don Cornwell's instrument, the laser-com instrument on the side. But if you look at the very top of the spacecraft, the small tube looking outward is the ultraviolet visible spectrometer. The neutral mass spectrometer is down on the mid-deck side of the spacecraft. And the lunar dust experiment is at the top above the neutral mass spectrometer. It's the sort of coffee can-sized thing that you saw at the top there. So those are the three instruments that are meant to address these two mysterious questions. And I'd like to tell you a little bit about how one of those instruments is actually going to operate. So the next video illustrates how the lunar dust experiment actually captures dust and analyzes it on its path around the moon. Basically, it will intersect and analyze any particles that are in its way as Laddie moves at 1.6 kilometers per second around the moon. These particles come in and create little charges that are then registered on a detector, and the size of those charges actually corresponds to the sizes of the grains that are being impacted. The neutral mass spectrometer operates in a very similar fashion, but it has a smaller aperture, and it's really aimed at looking for the gas particles, the atoms and the molecules in the tenuous lunar atmosphere. And it identifies those molecules on the basis of their mass, so you can identify things like calcium and titanium and iron that may be present in the lunar atmosphere, but we haven't measured them yet. We don't know if they're really there or not. And the final video I wanted to show you folks is actually takes us back to 2009 and the LCROSS mission. So this mission involved taking an empty Centaur launch vehicle and impacting it into the south pole of the moon into a location of permanent shadow and ultra cold. In places like that where there's no sunlight, it gets so cold that ice, if you can put it there, will last for billions of years without going away. And LCROSS was meant to check out whether or not that actually occurs. We had hints from Lunar Prospector, but it wasn't until LCROSS actually impacted the surface that we could actually see ice lofted up into sunlight, and the infrared spectrometer aboard LCROSS actually measured the features of the ice that was present there. So now we know there's ice there, but how did it get there? That's the question. And so you can imagine a number of scenarios that would deliver ice to the cold regions of the moon. One might be a cometary impact, but there's another possibility that slowly, over the millennia, molecule by molecule, water molecules have migrated, hopping across the surface of the moon, and finally some of them get cold trapped in these locations where there's no sunlight at all, and it's ultra cold, and they're stuck for basically forever. Laddie is in a perfect position to look at the possibility of water and hydroxyl, OH, in the lunar atmosphere. And so we'll be able to check that pathway, that water cycle, if you will, that takes the possible water from the mid-latitudes up into the cold traps. And the fourth instrument on the spacecraft is the Lunar Laser Communications System, a whole new way of doing business in terms of communications from deep space. And Don Cornwell will tell you about that next.
Thank you, Rick. I'd also like to take this time to thank the NASA Science Mission Directorate and the Laddie project for the ride to the moon that we're going to have for our technology demonstration. As Rick said, we're not actually a science instrument, but we are the Lunar Laser Communications Demonstration. We're going to demonstrate the first high-speed two-way laser communications, really for NASA and from the moon back to the Earth. And just as a point of reference, we are 6 times the bandwidth, the amount of data that we can send back in a certain amount of time, as compared to the most state-of-the-art radio system that was sent to the moon on the Lunar Reconnaissance Orbiter in 2009. And at the same time, we use half the weight and 25% less power, so we're more efficient. My first slide actually is an excellent illustration of the mission concept. It's very straightforward when you look at it. There's our optical terminal on the side of Laddie, and we're exchanging laser beams between the Earth and the Moon, and there's data imparted on each of those laser beams in the form of hundreds of millions of little pulses every second. So the next slide, please. So why are we interested in laser communications? So over the last 50 years, radio has served NASA very well for providing space communications, but like everyone else, NASA has needs for faster download speeds and to bring back our data, video, and images, high-speed, high-resolution images, and 3D high-definition video from satellites that orbit the Earth and probes going to the Moon and beyond. So light waves are much shorter in wavelength than radio waves, which means that we can pack more bits of data into every second on a light beam and also use smaller transmitters and receivers. And if you can play the animation, please. So, for example, the antenna on the left is a radio antenna. It's many tens of feet across. And on the right, the animation where you saw the ground terminal got smaller, that's our new optical communications ground terminal. It'll be based in White Sands. It again leverages the fact that light waves are shorter, and so you can keep the beams more collimated, more focused, and deliver more energy at a distant point. So we can get more bandwidth with optical communications using a smaller size and less power. Next slide, please. So we have an animation here that actually shows how our system will work. We have 3 ground stations. One is at NASA JPL. It's actually a site that they have in California. The European Space Agency has a site, and MIT has a site. So the ground beam from one of the sites will scan for Laddie around the Moon. And when Laddie sees that, it sends a pulse back. I'm a little bit behind on this. And then that causes the ground station to then lock its beam to the uplink beam, to the downlink beam. And then we start communicating. And we can send up to 20 megabits per second of data on the uplink from the Earth to the Moon, and then as much as 622 megabits per second from the Moon down to the Earth. And I'd like to again point out that MIT Lincoln Laboratory designed, built, tested, and delivered at both our flight terminal and our first ground terminal, and that we are partnering with NASA JPL and the European Space Agency for our other 2 ground terminals. And with that, I return the stage to Rachel.
Thank you, panel. We'll now open it up for questions here in the audience at NASA Wallops. If you'd have a question, please raise your hand, wait for mics, and state your name and affiliation.
Yes, I have a question about the laser communication system. If you increase the wattage, does it make it better, or is it just you only need that minimum wattage to make it at peak efficiency? I mean, is it like with regular radio? The bigger the antenna, the more the wattage, the better the signal.
So that's a good question. This is a certain design point. So we worked with the resources that we had available to us, and one of our, we have some limits in power. We're at the Moon, and we're on a small spacecraft, and so this is a design point that was chosen for the transmitter power. If the transmitter power were larger, you could, in theory, send a higher data rate, or more bits per second, or over a longer distance as well. That's right. Thanks for the help on the question. Yes.
Our next question also comes here from NASA Wallops. If you could please state your name and your affiliation.
Hi, Ken Kramer, Universe Today. I have 2 questions, please. First, for Don, can you tell us, I think the length of your experiment is restricted to 30 days or so after you get to orbit. Can you talk about why that is? And I believe also the spacecraft is going into an elliptical orbit. Why is it elliptical, not polar? Thanks.
Okay, so 30 days is what we believe is sufficient to do our demonstration. And we are along for the ride. It is a science mission, and we can't deprive our science team here of answering their very important questions as well. So we think we can do everything we need to do within the 30-day period. And we have a follow-on mission called the Laser Communications Relay Demonstration that'll be launched in 2017. It's a funded mission, again, based on MIT technology, but will be built at NASA Goddard, and that will be a duration of 2 to 5 years where we hope to really demonstrate long-term performance.
And I can take the question about the elliptical orbit. Even if you start off with a circular orbit, at low altitudes where we want to operate, it very, very quickly gets perturbed into an eccentric or elliptical orbit. And so it's just a question of managing those perturbations, which are induced by the gravity field of the moon, which is very irregular compared to that of Earth's, as we know from Grail now. So it's that which perturbs the orbit, and that changed orbit is something we need to adjust periodically. So every week or so, we perform a burn to attempt to basically sort of circularize the orbit and maintain periapsis, the point of closest approach, high enough so that, frankly, we don't crash into the surface of the moon. It's the lumpy gravity field that causes our orbit to perturb.
It's not the science.
The science drives the low point. The science drives getting as low as we can safely get with the spacecraft. Lower is better for Laddie. Lower is better because we've got two instruments that make in situ measurements. One's going for the dust, the other's going for actual in situ gas species. And so the lower you go, the more there are, the better your signal, the more you learn. But we'll be wandering around in altitudes as the orbit gets perturbed by the gravity field of the moon. We'll always try to get back to the low altitudes again. I hope that helps you.
Joe Pappalardo with Popular Mechanics. I'm just wondering if there's any, if you could describe some of the differences between the light and dark sides of the moon in terms of the exosphere.
Oh, sure. Actually, we've got a resident expert in the audience who made measurements of that very thing back on Apollo 17. Dick Hodges is in the audience, and I hope I do justice to what I found out. Certain of the species can basically freeze out on the surface as the night side, as you probably know, of the moon, since it's not in sunlight and there's very little atmosphere to conduct heat or to convect heat. It gets very, very cold. It gets below 100 kelvins on the night side just before dawn. That's cold enough so that when an atom or a molecule comes down and interacts with the surface grain, it basically chills down too. And so its residence time, that molecule's residence time on that grain, can become very, very long before it hops off again. And when it does hop off, it doesn't go nearly as high. So the atmosphere kind of collapses, or parts of the atmosphere can actually collapse at night. Whereas on the day side, it gets warm enough that these guys are hopping around. I think someone described it as like bunnies across the surface. That's a picture I won't be able to get out of my head very soon. But that's basically what the molecules of the exosphere are doing. They're hopping around. But their sticking time, the residence time on surface grains, is strongly controlled by the temperature, and therefore there's a strong day-to-night asymmetry.
Hi, just a question about the, given that it's a highly rarefied exosphere, what rate of detection are you expecting for the dust and for the elements? Are you expecting that to be fairly continuous, or just once every few seconds, or what?
That's a really good question. The density of the dust that we have in our requirements for measurement at about 50 kilometers altitude is a pretty small number. It's like only 100 or so dust particles per cubic meter. That's not much. I mean, that's way less than in my house, for instance. So running through that, however, at 1.6 meters per second, you can imagine smacking into those things with the aperture of LDEX fairly frequently. And so if the dust is there in that density, we'll see at a few counts per minute, possibly even higher rates, just how much is there. And if we don't see anything that says pretty much, we can place a very stringent upper limit on how much dust is actually there. But we'll know right away as soon as we drop down to those low altitudes. As far as, and the other instruments for dust detection, the ultraviolet and visible spectrometer can look at a distance and integrate over a fairly large column at whatever dust is there. The challenge that they have is for some of their measurements, they're looking against the coronal and zodiacal light of the sun. If you're looking back across the limb of the moon, you'll see not just the dust that's scattering light toward you, but also the zodiacal light in the inner solar system, plus the coronal structure as well. So it's a challenge, but they've shown they can do it. So we're looking forward to that.
So this is more of a practical question with the laser communication. What's the cost difference between a radio and laser comm system?
Well, we did a lot of development here to solve a lot of the issues that are, part of doing the complicated mission. So initially, it's expensive, but as we build more and more copies, we expect that cost to go down, just like for any system. So there's a lot of non-recurring engineering that happened for this project. Perhaps we can talk offline. Yeah. All right.
Is it on? Matthew Francis, Popular Science. Two questions. One is, how much dispersion is there in the laser beam between Moon and Earth? I know in lunar ranging missions there's a fair amount of dispersion. How big does the station need to be to reliably pick up the laser on the Earth end and vice versa?
Okay, so when you say dispersion, I think you mean actually the spread of the beam.
That's right.
So to speak.
Yeah.
So it starts out at 4 inches in diameter from the spacecraft telescope, and by the time it gets to the Earth, it's about 3.5 miles in diameter, 6 kilometers. So it's still large, but at the same time, it's a very small point when seen from the Moon. And one of the big challenges we have is keeping that pointed accurately over the entire time you're trying to communicate.
And the second question was about the dust detection device, and I'm not sure which of the two of you it should be directed to. But you mentioned that the size of the grain was correlated with the electric charge on it. So is that... You
want me to tell you a little more about that?
Yes, if you would,
okay.
please. I'm looking for...
Actually, when the grains come in, they impact that witness plate at the back end of the instrument, and they create a little plasma cloud. And the amount of charge that's created by that is controlled by mostly by two really important factors. One is mass, and the other is the velocity at which it comes in. And there are various formulae that relate those two things. But we know what the velocity of the spacecraft is, so that particular issue is taken care of, and that way you can look at the charge and relate it directly to the mass of the particle that's coming in.
Hi, John Pritchard, NASA social participant. With the Laddie science, with the study of the exosphere and the scientific results that come out of that, I think we're looking at evolution of the Earth-Moon system and then getting into some Earth science. So what can we point to in Earth science that we could learn about in future from this work? For example, is it possible to learn something about Earth's magnetic field?
Okay. I'm not sure I follow where you're going with that question. We've measured the terrestrial magnetic field multiple times with very, very high precision.
Formation, dynamics, formation and maintenance.
Okay. Well, okay, but the Earth and the Moon have evolved down two very, very different paths since their birth together, roughly 4.5 billion years ago. The Earth has retained and accumulated more volatiles, hence oceans and things like that, and that along with its very, very active geologic processes have really sculpted and changed the surface of the Earth. We've got continents that drift around because the mantle is convecting. There's an interior dynamo that gives rise to the magnetic field that constantly change the surface of the Earth. The Moon, on the other hand, has one geologic process going on today and one only, and that's impacts. Asteroids come in and they smack into the surface of the Moon and they create craters. So material is excavated and redistributed around, but they're really different worlds. Fortunately for us, and fortunately for the Russians, the impacts don't occur very often on the Earth. They're happening all the time on the Moon. Now, that said, there's one other aspect of this that's kind of interesting. If the moon has maintained this low obliquity, this very low inclination, the Earth's inclination is 23.5 degrees, that's why we have seasons. The moon really doesn't have seasons. It's a very stable system. That means the locations at the North Pole and the South Pole, some of those locations are in permanent shadow. That also means that stuff that has been delivered to those locations from the earliest times of the solar system is still there. That's stuff that was delivered to the Earth in the earliest times of the solar system too, but it's been lost. The stuff that was delivered in the very earliest times has been lost by those same geologic processes I was just talking about. The geology covers it up. It's gone. We can't recover it anymore. The moon is still there. It's still sequestered. So if we go there to the poles of the moon and start digging this stuff up, we might be looking at the prebiotic materials that gave rise to life on Earth, the same ones.
Thank you. We have time for a few more questions.
I have a real quick question, and it involves what do we know about the moon's outgassing, and how does that tell us about the interior and its state of evolution?
Is it fair for Jim Green to ask questions like this? We do know that argon-40 is outgassing from the interior of the moon. That was the experiment. That was one of the experimental results that Dick Hodges over there sitting in the audience got back in the 70s on Apollo 17. Argon-40 comes from radiogenic decay of potassium-40, of which there is a fair amount on the moon. We see it actually in distinct locations on the moon, and it's really strongly related to the crustal history of the moon and the interior history of the moon. Another thing we observed that some of which may be coming out of the interior and should be expected is helium. But it looks like, based on LRO results, that the helium that is seen in the lunar atmosphere mostly derives from the solar wind. So that's something that's coming from the outside in. Now, more about the interior of the moon, there may be other things that are leaking out. Argon-40 gets out because it's a noble gas and it doesn't chemically react with anything. Other substances, such as water, may not be so lucky. There may be juvenile water still in the interior of the moon. In fact, mineral samples have revealed the presence of water in those earliest minerals, apatite grains. And I'm getting way deep into the science of that, but the water probably would have a hard time getting out because it's so reactive. So anything we see near or on the surface either was excavated, delivered, or migrated from low latitudes and got cold trapped.
Thank you. We have time for one more question from social media or media here in the audience at NASA Wallops.
Oh, man.
If Jim Green can ask a question, I guess I can too. Of course, the Apollo astronauts left lunar corner cubes, reflectors on the surface of the moon, and we've been pinging them with lasers for years to measure the Earth-Moon distance. The laser comm in principle also is a ranging instrument. How much more accurate? Now, of course, Laddie's in orbit. How much more accurate will the laser comm give us a measurement of distance to at least Laddie than the lunar reflectors?
Well, we're really good at measuring relative changes in the distance along the path, and we're working with some of the science folks at NASA to see if we can turn that into absolute range measurements. But we know we can measure relative changes down to the centimeters. And with a lot of averaging, the variations in maybe microns per second even is what's been discussed. So there are a lot of variables when you're actually doing the ranging. You have to account for the atmosphere and what that does, because sometimes the path length changes there. And so, but as I said, we're working with them to see what we can back out to be able to get absolute range measurements. But centimeters is the answer.
We have time for one more question from a member of the social media team
Somebody not
or
from headquarters?
news media here in the audience.
Hi, I'm Miriam Kramer. I'm with Space.com. And I was just wondering, are there engineering implications that could potentially come from the science of this mission? For instance, something having to do with a lander or even probes to various asteroids or Mercury. Yeah.
Want me to take it? Okay. I feel like I've been talking a lot. But if you're asking about what the science instruments can bring to future exploration, well, there are similar problems at other bodies. We'd love to know whether lofted dust occurs at larger asteroids, whether lofted dust occurs. We expect that if it happens at the moon, it happens elsewhere as well. So sending similar instruments to those bodies will confirm and further inform us of that physical process, as exotic as it is. So you can make second use of anything that you develop for spaceflight, but I was wondering if you were going in a different direction with maybe the reuse of the Laddie common bus, the modular bus design.
Oh, no, you actually got it. That was
Okay, all right.
Thank you.
Okay, I'll stop there then.
Thank you, panel. That concludes today's science briefing about the Laddie mission. You can learn more about the mission by visiting us online at nasa.gov/Laddie, or by following the mission on our social media, including Twitter at NASA Laddie. And tune in tomorrow at 9:30 p.m. Eastern when NASA TV begins its live mission broadcast, and launch is scheduled for 11:27 p.m. Eastern. I hope you'll tune in, and thank you for joining us.